Now, let's say we are taking a walk. And let's do an above view. Above view, that's great. So we're up in the sky, we're looking down at somebody, and let's say they go first 10 meters east, then 6 meters south. So a person walks 10 meters east, then 6 meters south. Now I'm going to call this then vector A, and I'm going to call this vector B. And I can draw those vectors separately again. So 10 meters east, so vector A would be your 10 meters east, vector A. Now again, I should probably really, measure this and say, okay, well that's going to be worth 10. Whatever scale I want to use, that's worth 10. You gotta do it to scale. Matter of fact, maybe for this example I will. Maybe I'll make it, let's see. Let's go, you know what we'll do? We'll go to 50. That's fine, we can double it. So, let's really overdo it here. And I'll make vector A worth the neatest I've ever done, but that's fine. So vector A, here we are. That's still worth 10. My scale's 50 centimeters, so we can scale that appropriately. And if I want to do vector B, using the same scale, well, it's 6 meters, so I'm not going to use all 50 centimeters, since I'm only going to use I can talk. Since I'm only going to use 3/5 of that, I'm going to use 30 centimeters, and that's going to be my vector B. So vector B is going to be about 30 centimeters. I'm going to draw vector B right here. Vector B. So somebody walked 10 meters east, then they walked 6 meters south. Now, this doesn't give me a picture of this particular person's overall or resultant displacement because I haven't put these vectors together. Now, obviously, as the person walks, once they reach this position, they're going to pivot and turn downward. So I have to place these vectors, again, what we call head to tail, to add them. So I'm going to redo the picture over here. And again, this is called addition by graphical methods. I will put vector A over here. About right. It's a little messy. And then I'm going to take vector B. I'm going to apply it. Now I got to try to keep that 90 degrees. That's where graph paper comes in handy, or you can use a protractor because east and south are 90 degrees from each other. And that's vector B. And I should label them appropriately. The resultant is from the start of your first vector. The person started here, and they ended up here. And that's where my arrowhead's got to be. So again, you take the two, what we call, legs of the trip. We put those legs, or vectors, head to tail. It makes sense. I walked, I turned, I went down. And then, of course, this here is the displacement, the overall displacement, the resultant. The person started here, they ended here. It wasn't their pathway, but it was their resultant. Final minus initial. Now, in order to find this resultant in this particular case, this resultant obviously is not 4, like it was in the previous example. We definitely did not have a resultant of 4. It's much different. Now, some of you are thinking, well, I can just do it. 10 and 6, I can do Pythagorean theorem and find the resultant, which is true, you can. We're going to get into that later. But not every time are we going to have a nice right triangle. But since we started this by actually doing it with the proper scaling, we can, with proper measurement, we can use our scale and measure this. And we can see that it's about 60 centimeters. And that's going to be about 12-ish meters. And not only can we do that, now that may be off a little bit because my scaling may be off a little bit. That's not an exact number, and if you use a scaling technique properly, you can get a more exact number. As a matter of fact, if you do Pythagorean theorem, you could do it. So it would be a squared plus b squared is c squared, so we have 100 plus 36, so root 136, which, I don't know exactly what that is. We'll find out. So 136 square root 11.67. We're very close to 12. So our measurement, doing the direct measurement by graphical methods, isn't that bad. And then we're going to measure this angle, and we have to measure it appropriately with the protractor. And I can see that my zero line is here, and I'm going to go 10, 20, a little less than 30 degrees, and I got big marker here, so I don't know exactly what it is. It's about 30 degrees. It's probably a little less. Can I find that via trig? Yes, I can. Am I going to do that right now? No, I'm doing it this graphical method. But trust me, when we get into problems, you're not going to be sitting there with a ruler and a protractor. We will show you how to do it mathematically. That's where we're going. But this is the theory right now. And then when we write the resultant, we have to write it accordingly. The resultant is about 12 meters at 30 degrees south of east. I definitely went 12 meters as a resultant, as a displacement. I'm about a little less, probably 30 degrees. But that 30 degrees was measured from here and sweeping downward from this axis. So remember, I started on the east axis, that's my reference axis, and I swept downward south. Now, the wild thing is that vectors, when they're added, can be added in any order, so that instead of doing A and B giving me the resultant, in theory, the way vectors work is that A plus B is equal to B plus A. And they will both give me a resultant. That means I could have, instead of going 10 east, then 6 south, I could have gone 6 south, then 10 east. And it would have ended up in the same place. And that's absolutely true. Because if I take this diagram, this, and let's say instead of going this way and here, let's say I started here, went south first. Which I could do. Go here, go to the start, go down south about 30 degrees. That would be vector B. And then let's go over east, which is, you got it, there it is, 50, so it's going to go right across. And again, I added those two vectors. I added A and B, or B and A. I added them head to tail. Head to tail. The start of the second vector starts at the end of the first vector. That's vector A. Sorry about the sloppy writing. And note, you would have, if we did that, we would have come up with the same resultant. Some books call this the parallelogram theorem because it makes a parallelogram to find that same resultant, which is fine. But all you need to know is you can add them in either way. Typically, I personally, just a preference, add the x-axes vector first and then the y-axis, because that gives the angle measurements a little more, it gives them a little more, it makes them a little easier to work with, especially later when we get into the math with sine and cosine. Regardless, though, if you were to do this first, you wouldn't have had this. Our resultant would have been the same. Our resultant is still 12. But note our angle that we measured before is not there. We now have this angle. By the way, you always measure the angle off of the tail of the resultant. You're not going to measure the angle off of the end or the head of the resultant. It's not where you started. It's always off the measurement is always off the tail. And then I have to measure this again. And if I measure this, I go over here, 90, going all the way out to about, going beyond, let's see, beyond, going to 30. So that's about 60 degrees, which makes sense because it's complement to the previous angle. But that does change the way we represent r. In this particular case, r doesn't equal, well, it does. It's 12 meters at 30 degrees southeast. But the way I drew it here, r is equal to 12 meters at 60 degrees. Now watch this. 60 degrees, this is east of south. Because I used south as my reference axis. And I swept out towards the east direction. So these say the same thing. They're identical. It's the same vector. It's the same displacement at the same direction. We're just using two different reference points to measure that direction. Now, when you do this, 12 meters doesn't get a positive or a negative sign. Because previously, if 10 meters east, we'd say positive 10 meters, because it's along the x-axis, or 6 meters south, we'd say negative 6, because it's south, but it's pointing downward. So when you're on an axis, you can use plus or minus, because it's like a number line. I'm going plus direction, I'm going minus direction. But when you're at an angle in any of the 4 quadrants, plus and minus is out the window. You can't use it because it doesn't properly represent the direction, because you need the angle. So the plus and minus designation only works on the x and the y axes. If you are in a quadrant, you're going to give the value or magnitude of the vector, and instead of plus or minus, the directional indicator becomes the angle. And you need to use that. And that's the best way to do it. Now, you can do this with not just 2 vectors, you can do this with a ton of vectors. And the vectors don't have to be nice and at right angles. So we'll go over that and show you another example in a few. Let me reset the board.